tell you why. So to tell you why, I think I want to okay, so I want to tell you the convergence of this iterative method. It is so first of all, I want to say it is different from the concept of convergence of numerical schemes. In numerical schemes, we are talking about the analytical solution minus the numerical solution. Here, we are talking about the difference between u at step k minus u exact. And exact is not the exact solution of the differential equation. It's just the exact solution of the ax equal to b, au equal to b. All right. Okay. Where a times u exact is exactly equal to b, while this uk is just a part of the iteration. Okay. Now, this is, of course, this depends on k. So I also put a superscript k. Now, if I write down the Jacobi iteration, which is which is d times uk is equal to b minus l plus u times uk minus 1. All right. And I'm also going to expand the a here in the exact solution. So d times u exact is also equal to b minus l plus u times u exact, because a is equal to d plus l plus u. Right? Agree? Now, what happens if you subtract these two equations from each other? What happens if you subtract the left from the right? The left-hand side would become d times what? D times ek, exactly. And what happens to the b? It cancels. And I just get minus l plus u times what? ek minus 1. This is the evolution of the error. Okay? Or I can write like ek is equal to minus d inverse times l plus u times ek minus 1. This is how the error evolves. This is how, okay, when k is equal to 1,000, this is what ek is. This is E1000. And if I write down this matrix as R, okay, I mean, because this is just D inverse times L plus U. Well, let's put the minus sign also in. Let's say this is equal to R. Then I can say this is R times EK minus 1. And EK minus 1 is also equal to R times EK minus 2. So this is equal to R squared times EK minus 2. Is equal to, etc., is equal to what? Times E0. R to the kth power. Right? And what is E0 in our example? It's minus U exact, right? Right? Because we set U0 to be 0. So E0 is minus U exact. Our solution area EK is just the U exact, whatever it is, multiplied by this R matrix for k times. Okay, so two questions. One question, this is a linear algebra question, so nothing to do with numerical methods. So what property does the matrix R need for the solution area EK to go to 0? Yes, I see him. Eigenvalues of R should be smaller than 0. absolute value of the eigenvalues of R should be smaller than 1. That's right. That's right. So if I compute the eigenvalues of R, all the eigenvalues has to have a magnitude less than 1. If there is one eigenvalue with the absolute value greater than 1, what is going to happen? That particular corresponding eigenvector is going to become bigger and bigger and bigger and bigger as long as my E0 has a non-zero component in that direction. My EK is going to explode exponentially. I'm going to diverge instead of converge, right? So the convergence of Jacobi requires all the eigenvectors, all the eigenvalues of the matrix R to be having magnitude less than 1. Okay, second question. After a lot of iterations, let's say k equal to several thousand, do we know what EK looks like, even if you don't know what E0 looks like? What is going to tell you what EK looks like? Yes? The largest eigenvector of R? Eigenvalue? So if I can expand E0 into a summation of AI times Xi, where Xi are the eigenvectors, all right, then my EK would be equal to what? Is equal to summation of AI times R to the K power times these Xi's. And what is, if Xi are the eigenvectors of the matrix R, corresponding to eigenvalue lambda I, what is R to the K power times Xi? Yes, that's lambda I to the power K times Xi. Okay, and no matter what AI is, I know that when K is big enough, the dominant component of this summation is going to be the lambda I that has the largest magnitude, or have a magnitude closest to 1, assuming the method converges. So why would the solution error look like that? Because that's probably corresponding to the Xi, whose corresponding eigenvalue is closest to 1. And we're going to discuss next lecture why that is the case for Poisson's equation. When we do Jacobi iteration, when we derive this R for Poisson's equation, why does the slowest decaying eigenvalue has an eigenvector corresponding to the smoothest possible solution? All right. Okay, so I will see you next Monday.